Hello friends! So today's topic is counting. It's going to be fun. I'm going to teach you how to count all over again. The trick is that we're going to tie everything back to set theory. All right, so a lot of these things that I'm about to tell you, you have seen before in like a high school math class or something, but you never saw it from the lens or through the lens of set theory, and that's where we're going. All right, there will be more things to build on top of as well. But let's talk about the sum and product rules. Those will sound very familiar to you, and we'll tie them back to finite set theory. Okay? So here's the first one, a product rule. Let's say that you probably heard this sentence before, right? If there's A ways of doing one thing and B ways of doing another thing, then there are A times B ways of doing both, right? It's like, got this many options for the first thing, this many options for the second thing. You're going to want to do both things. Like you choose one thing from A, got A options, one thing from B, got B options. A times B total is a way of performing both actions. And you can think about this in terms of sets and their Cartesian products. Because if you want to choose like one thing from a first set and another thing from a second set, you're building a pair, right? In general, you're building like a Cartesian product, right? An element of a Cartesian product set. So, and like the things that you get, what's the size of a Cartesian product set? It's the size of their individual pieces. Like you got A1 choices for the first one, size of A2 for the second one, all the way down. So let's have an example with sets. Let's say that you go and you get ice cream. All right, so you go to an ice cream shop, and you can think of like your choice for your ice cream and like your toppings in terms of two sets. Like, all right, what's your ice cream choices in this shop? Maybe it's vanilla, chocolate, and strawberry. Very simple ice cream shop. All right, so those are your ice creams, and let's say that you want to choose ice cream and then also like a topping, and so maybe there's only sprinkles as toppings. So like what are your choices for toppings? There's sprinkles or no sprinkles. So those are two sets, right? You can think of those as two sets, and what you want to do is like, I want to choose ice cream and sprinkles, right? Some kind of ice cream and some amount of like either sprinkles or no sprinkles. I want to choose an element of a pair, right? An element of the Cartesian product of these two sets. Does that make sense? Like your choice, your option, every one of your choices, whichever one you choose, is an element of I cross S. Does that make sense? Like my favorite choice here would be vanilla with sprinkles. Do you see how they're all an option under the Cartesian product? If I can spell sprinkles. It's like pick one thing for the ice cream, pick one thing out of the second set. How many options total? Well, you got three things for the first one, right? The size of the first set, times two things for the second option, right? That's the second set. So there's 6 options total. Does that make sense to you? Do yell at me if you have any questions about that. It's like, all right, it could be vanilla sprinkles, vanilla no sprinkles, chocolate no sprinkles, strawberry no sprinkles. That's just your options are an element of our Cartesian product set, and if we want to count how many options total, we want the size of like that set, which ends up being the size of each of those individual sets multiplied together. It's got that many options, size of A1 options for the first one, size of A2 options for the second one, second element of the tuple. So yeah, that's the product rule in set theory now. Some rules even easier. So like, all right, if you have A ways of doing one thing and B ways of doing another thing, and like you get to choose like one out of those ways, you can't do both at the same time, there's no overlap, then there are A plus B ways total to pick something to do. Like you got A things over here and B things over here, you got to pick one thing, like you got A plus B choices total. That you can bring back to sets as well. It's like, I want to choose something out of a union of sets, right? Some options over here, some options over here. Like, what is the size of all my options? It's the size of their union, yes? And if there's no overlap, that's just the size of individual sets added together. So let's say that, like, I don't know, you're bored during the summer and you want to choose something to do. You can think of your choices in terms of like outside options and inside options. Like, I want to do an outside activity. We can choose from set X, like hiking or swimming. You can always tie it back to set theory. Or you want to do an inside option. What are some inside activities? Like, let's make another set. And these are disjoint sets, by the way. You could watch a movie. You could eat food. Those are some indoor options. And if you want to choose something to do, it's like you're choosing an element from the union of these two. Does that make sense? And so that's going to be like how many options total. It's just like the size of this one plus the size of that one for total. All right. So in general, it's just like what's the size of a bunch of union of sets that are like disjoint. It's the size of their individual, it's the sum of their individual sizes. That's the word. All right. As long as there's no overlap, at least. And that finally brings us to a new kind of rule. Maybe you haven't heard this one before. It's the bijection rule. If we have a bijection, so a bijection, an invertible function from one set to another, like we have some function that's taking like s's to t's, then those two sets better be the same size. All right, that's the idea. They better be the same size. They have the same cardinality. So like, let S and T be two finite sets. If we have a bijection from S to T, then their sizes must be exactly the same. That's the only way we can have a bijection. Because think about it. Like here's S. You have to, if it's a bijection, it's 1-to-1, right? There is nothing that it's like mapping to twice. Like maybe there were only two things, you kind of be forced to do that, right? And that's suddenly not 1-to-1 anymore. Does that make sense? So that's not a bijection because of that. Like there can't be just two things. There have to be exactly three, because if you think about it, it's got to be 1-to-1, right? Something goes to something else always, and then also onto the entire set needs to be hit. And so there's always, like, for one thing, it's hitting some other thing that's never been hit before in the other set. So that's forcing it to be the same size if they're both finite sets. Does that make sense? So like if you know that you have an invertible function from one set to another, you know that their sizes must be the same if they're finite. Okay? And that's going to give us some cool ideas later. But I think that's what I wanted to say. So yeah, a times b ways, a plus b ways, for the product rule and the sum rule, and a bijection, you know that they have the same size. Okay, so we can now generalize that product rule, and I know that I learned this once upon a time in high school, so you've heard it before, but again we can bring it back to set theory in general, because really you're building up like some interesting sets. All right, so here's my silly example. Let's pretend it's the Olympics, and there are 15 contestants at our cat meme Olympics, and so the question of the day is, how many different ways are there for somebody to win? Like, how many different ways are there? You've got a gold medal, a silver medal, and a bronze medal at these Olympics. And how many different ways are there going to be to give out these medals to the 15 contestants? All right, so like you've got 15 cat memes all lined up trying to win best cat meme. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 12. Let's assume that's 15. And then if you think about it, it's like, all right, you got all these guys. Think about it in order. Like, who's getting gold? How many options are there for people who get gold? Well, there's 15, right? Because you got 15 total. So like, let's say that this person gets gold. There's 15 people who could get gold. And then now there's suddenly, you can't also give silver to that same person, to that same cat meme. So that leaves 14 people who could win silver, right? So like maybe this guy over here, this meme gets silver. And then now you've made two choices. So you only have 13 left to win bronze. All right, and anybody could win these, and we want to like try them all. So in general, like you're gonna make 3 separate choices, right? It's the product rule, it's the generalized product rule, we say. It's like 15 for the first one, 14 for the second, 13 for the third. So that means if you multiply them together, that's how many different ways there are to give out medals. All right, assuming like everybody has a chance of winning, everybody could be winning gold. So that's the idea. You can just multiply them together. You got to subtract one because you've made a choice, right? You made an arbitrary choice, but you made some choice. That's the generalized product rule, and that's useful for counting things called permutations, which you may or may not have heard of before. So that's where we're going. All right. So before we get there, though, I have a question for you. All right. So using these ideas, use like the generalized product rule. Here are some sets. Here's a set of digits. Like pretend these are characters of a password. You can use a digit, you can use a letter to make your password, pretend it can only be lowercase. And then here are some special characters that can appear in your password, nothing else. So what I'd like you to do is give me the number, compute the size, right? Compute the number of passwords that satisfy these constraints, all right? So I want you to think of all the ways to make passwords out of these characters where the following constraints apply. So the strings that are your password can only be length 5, 6, or 7. This is very easy to crack, I guess. But your password can only be length 5, 6, or 7. So 5, 6, or 7 characters taken out of these. And then the characters can be anything, special characters, digits, or letters, but the first character can't be a letter. So it can be a special character or a digit. It cannot be a letter. Does that make sense? All right. So try to come up with the size. How many total password options are there with these constraints in mind? It's going to be uses of these guys, like product rule, sum rule, generalized product rule, perhaps. See if you can try it. All right. Let's think about we can break it up into like, all right, what are all the possible passwords of length 5, 6, and 7, like separately? Like, what are all the length 5 passwords? If I can spell length. I'll make a set called length 5 that holds all their passwords, but really I'm only interested in the size of that set. What's the size of all the length 5 password sets? So, okay, what are all the length 5 passwords and how many are there? So, okay, it's going to be a use at the beginning of, like, the first character, right, can't be a letter. So it's got to be either a digit or a special character. And so how many options do we have for the first letter? Well, it's going to be the size of digits plus the size of special characters. Does that make sense? That's your first character. First character. That's how many options you have for it. It's like, all right, it could be a digit or a special character. It's just the size of those. That's the sum rule, yeah? And then after that, you've made that choice. Then you want to make a choice for the remaining 4 digits, right? Because this is a length 5 set. So you made the first character choice. It's going to be now the product rule, right? You want to make the choice for the first character, and then you want to make 4 separate choices for the rest of the characters. And so it's going to be like, all right, anything goes for the rest of the characters. It could be a special character, digit, or letter. So it's going to be, all right, digit, either it's a digit or a letter or a special character. So for the next character, you have all these options, right? The size of each of them. Does that make sense? You have that many total, all those different things, the size of them. And you're doing that 4 more times for a length 5 password. Does that make sense? So that will be your answer. So those are, like, this is how you can choose from all the other 4 characters. The other 4 characters. And none of them influence each other, so like you just take that to a power. It's just the product rule. Like you're making a choice for the second one, choice for the third one. That's what's going on. You're really, like, a string is just a Cartesian product of characters, right? It's a tuple. So yeah, I think that's what I want to say for length 5. Length 6, you can imagine, is exactly the same. Like, what's the size of the length 6 password set? Whatever it is, well, the first character, again, has to be a digit or a special character, so it's the size of those. That's how many options you have for the first character. And then for the other characters, it's, again, going to be your multiplying product rule. It could either be a digit, special character, or a letter. And let's try to keep it consistent. Digit, letter, or special character. That's the amount of options that you have for each character after that, and you have 5 more in a length 6 string. Okay? So your final answer then, you do that for length 7 as well. It's going to be like, all right, the size of the length 5 set. Length 5 plus size of length 6 set. Plus the size of the length 7 set. And I have not done the math, but I think you can easily do that math at that point, yeah? So there's that one. Try that, and then, so this is, honestly, that was just an example of the sum and the product rules, right? No generalized product rule yet. Here's one that's going to need the generalized product rule. So here, I'll go stare at this slide for a second. Here you go. So in California, at least for now, we're about to, like, maybe you're watching this recording after the rules have changed, but the rules for now, at least at the time of this recording, is in California, the uncustomized license plates look like this. It's a digit, letter, 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 and then digit, digit, digit. So there's 7 things total. So it's digit, 3 letters, then 3 digits. We're on the 9s right now for the first digit, though, so it's about to, they're going to figure out something else to do. We'll see. We'll see in due time. But my question is, how many license plate numbers are possible if no digit or letter appears more than once? Assume that that's a constraint. It's not an actual constraint for real California license plates, but pretend. What's going to happen? How many license plate numbers can you have that follow digit, 3 letters, 3 digits, if you cannot repeat things? So give that a try. So for example, like, this is a valid license plate number according to those rules, 6XYZ789. It's supposed to be a Z and not a 2, 789. But, like, that's allowed, but this one wouldn't be allowed, like 6XXZ 689. So that's not allowed because, like, you got 2 6s, 2 X's, like, you cannot duplicate things under these rules. All right, so if you think about it, well, how many digits do you have to choose from at the start, at least? If the first thing's a digit, how many digits do you have for the first digit to choose from? Like, you're picking, like, to fill in, you got 7 blanks. The first blank you want to fill in with a digit. How many options do you have for your first digit to choose from? Well, you got digits 0 through 9, which is 10 digits total, right? So the very first choice is 10, right? You can put a 1, a 0, anything goes for the first one, and then you can never use that digit that you chose ever again, all right? And then you have to start counting down. And then same for the size of, like, then it's time for a letter. Like, you got to fill it in, the next thing with a letter. How many letters are there to choose from at the very beginning? Well, 26, right? So then you have 26 options for that letter, but then for your next letter, you're going to fill in the next blank with another letter. You can't use that thing again. So maybe you just chose an X, you cannot choose another X. Does that make sense? So now you got 25 options. And then likewise, you've chosen 2 letters now. You want a third letter. You now have 24 options to choose from. See, that's going to cover all your bases. No matter what you pick, like you got 24 left. And then same for the last digits. That's supposed to be a 4. For your last digits, you got 3 digits left. Well, you've chosen one. Like whatever one that was, can't choose it again. So you get 9 left for that one, 8 left now. And then you've now chosen 3 digits. You can never repeat them, so you have 7 options total for the last one. Does that make sense? 7. And so whatever the number is, that's the number. Whee! Those are your options. I hope that makes sense. So that's the use of the generalized product rule. Okay? And that leads in nicely to permutations. All right? So a permutation, if you haven't heard that before, it's a sequence that contains every element of a set just once. All right? There's another thing called an R permutation. Just a normal permutation without the letter R is just a sequence that contains each element of a set exactly once, and that set is finite. All right? So yeah, we can talk about the permutations of any set, and they are, like, let's pretend we have a set A. The set will hold numbers, let's say. So A is the set 1, 2, 3, 4. We can talk about all the permutations of A, and that it's just a tuple, right? It's just every jumbling of all these elements. Like, for example, 2, 1, 3, 4. That's a permutation of A. Does that make sense? It's going to be a tuple. It's like, all right, give me a jumbling, so give me a tuple. A permutation. This is a permutation of the elements of A. Does that make sense? So, well, it's another permutation. Like, you got to use them all. So, like 3, 1, 2, 4. That's another ordering of all the things. Okay? So, in general, there are n factorial different permutations because that is the generalized product rule all over again. Because if you want to permute things, like you want to fill in for a size 4 set, you want to fill in a size 4 tuple with, well, 4 factorial things. You 4 factorial options because you got 4 options for the first thing you fill in, because like anything goes. Then you've chosen something, so there's 3 things left to choose from, 2 things left, and then your hand is forced for the last one. Just 1 option left after that. So that's why. Does that make sense? I hope that makes sense. So that's a normal permutation, just like you're permuting everything. You're jumbling every single element. You can also talk about jumbling just a couple elements, like taking a handful, but not everything. An R permutation is a sequence of R items, right? It's like a tuple of R items with no repetition still, but they're all taken from the same set, all right? So an R permutation. So let's talk about let's say we choose a couple things out of A. It's like choose only 2 things, like a 1 and a 4, for example. So 1 and 4, that tuple that pair is we call it a 2 permutation. Does that kind of make sense? It's a 2 permutation. We're taking 2 things out of the set. 2 permutation of A. And what are some other 2 permutations? So are like 2, 3 is a 2 permutation. 4, 3 is just like 2 elements. No, can't grab 2 things twice. Can't grab the same thing twice. 1, 2. There's a bunch of options. All right. So those are R permutation. You're just taking 2 things. Just taking 3 things. Just taking R things. All right, so we want to count. It's not going to be as easy as just a factorial anymore. Like how many R permutations are there in a set with n elements? We can write that as PNR. How many permutations? How many R permutations are there in a size n set? That's how you read it. So PNR, it's the number of R permutations from a set with n elements, and it just so happens that there is a formula for that, and we can work out this formula in just a second. But what we want to just decide is like how many ways are there to choose 2 things? How many 2 permutations are there out of A? So we're asking like what is P42? That equals, if you think about it, well, you've got 4 options for the first element of your pair, right? Because it's a size 4 set. And then for your next one, you got to choose something else. So there's 3 options left. So the answer is 12, right? In general, so the answer is 12. There are 12 2 permutations of our size 4 set A. But there is just a formula if you want to memorize the formula. It's n factorial over n minus r factorial. So we can get that in the other way. It's like 4 factorial over 2 factorial, because what's 4 factorial but 4, 3, 2, 1? And then 2 factorial is 2, 1. See how that's going to nicely cancel the other things. That's perfect. So there's a couple ways to get at it. I like just like thinking about it like that. That's easier than memorizing the formula for me, honestly. And so in general, if you want the number of normal permutations, that's like how many n permutations from a size n set, pnn, and that's going to do it, right? Because like n minus n factorial is 0 factorial, which is just 1. So it doesn't do any canceling at that point. So yeah, in general, remember that a particular permutation has an order. So order matters. It's a tuple then. It's an element of a Cartesian product set. All right. That's permutations, and so here's an example of that. Here is a funny story from a while ago. Back in South Africa, they had a lottery. It was like a state-run lottery, and they, like the cops had to show up to the lottery offices because they did not believe that what happened. So they were investigated after these numbers, 5, 6, 7, 8, 9, and 10, were drawn in that exact order. And there were 50 balls. Like if you think about a lottery, it's just like you got a bunch of balls in a hopper, I guess. And like they're picking out balls with numbers on them. And they picked out 5, 6, 7, 8, 9, and 10 in that exact order. All right. So like what are the odds of that? Because they could have picked, right? They're picking 5 things, 5 balls of like numbers with 1 and 50 on them. Like they could have picked 50, 42. Like that's a valid 50, 42, 1, 8, 7 or something. Or sorry, there's 6 options, aren't there? 6, not 5. My bad. 1, 8, 7, 23. Like that's a valid option. There are a million different options, right? More than a million for how to draw these numbers out of the lottery. And they just so happened to choose 5, 6, 7, 8, 9, and 10 in that exact order. That's very unlikely, right? It kind of screams somebody's set things up. So let's see what the probability of that should be, right? So it's going to be 1 over how many ways are there to choose numbers out of this lottery. So that's P 50, 6, right? We're choosing a bunch of 6 permutations from a size 50 set. Because there's 50 lottery balls that are all jumping around. Number of lottery balls. And then there's 6 things that we're picking. 6 numbers to pick. Number to pick. And so if you think about it, like 50 options for the first one, 49 options for the second ball, all the way down to 45. 1 over that, right? Because this is just one option of many. What are the chances? 1 over 11.5-ish billion. All right. So, I mean, it's a non-zero chance. Technically, with enough lotteries, this will happen by chance, but it's very, very unlikely. So they think that there was some foul play, which is interesting, right? So here's your turn to use this idea. So here's a question that involves some ideas. So 10 members, let's say that you're at a wedding, 10 members of the wedding party, they are lining up and they want to take a photo. But they want to make sure that, of course, the bride and groom are together for this wedding. So they're going to try and keep them the same. And the question is, how many ways are there to line up the 10 people if the groom, like we got to get their good side. So let's say that the groom has to be immediately to the left of the bride in the picture. All right, so you can put them anywhere as long as the groom and the bride are next to each other. So like pick an order. Who knows where they are, the groom and the bride, but they better be, like the groom better be to the left of the bride. All right, so here's the groom, here's the bride, immediate left. They got to be just like that. And then everybody else you can place in other places. All right, so think about that. What are your options? How many total? Count them. All right. Do you see it? Well, if you're forced, right, it's like you're filling in a bunch of blanks, right? It's like who goes first, who goes second, who goes third. You got a bunch of options. But if you think about it long enough, the groom and the bride, they're acting as a unit, aren't they? They have to be in that exact order. So the way that you can solve this problem the easiest is to just think about like these two people together as one. Count as just one person, one thought, right? Because they all have to move together. Does that make sense? Count as one person. And then it becomes easy, because now you're just jumbling 9 entities, yes? Because the groom and bride are now together. There's 9 things total. So how many options for who comes first now? It's, well, 9. So you got 9 things, 9 entities. Either the groom and the bride are there at the very left side, or you got somebody else. And then you have 8 options left, right? 7, 6, 5, all the way down to 1. So you're just jumbling 9 things, and so there's a permutation on 9 entities at that point. Does that make sense? So there's 9 options total for who comes first, where like who is now put in quotes, I guess. Options for who in quotes, because really it could have been the groom and bride together. Who comes first? Does that make sense? Cool idea. Did you know that? Who knows? Now you do. So there's that. And yeah, so that's an example of permutations. Let's also count subsets, right? This was counting like orders, jumblings, permutations were all about that. Counting subsets is how many ways are there to like make choices and the order doesn't matter, all right? Make choices and the order doesn't matter. So let's think about this. How many subsets of a set of size 5 are there? That's interesting, right? We're asking for the size of the power set, right? So that's a little hard, but we know that it's to the 5th power, right? So you got the power set of A. What is that? So you got the empty set. You can choose nothing. You can choose like you can choose just one thing, right? All the size 1 sets. So like if this is the set A, like you can have just the set with 1 in it, just the set with 2 in it. It's very hard to draw curly braces as usual. All the way, right, to the entire set. Got a bunch of options. 1, 2, 3, 4, 5. So how many things are there in the power set? What's the size of the power set? For a size 5 set, it's to the 5th power, 32 elements. And so we can then go and think about, like, all right, how many let's talk about subsets of a certain size. How many subsets of A are just size 1? Think about that. Well, you got 5 of them, right? Because you can have just like, you're putting one thing in the set, you got 5 options, yeah? So the set with just 1, set with just 2, all the way to the set with just 5. There's 5. Does that make sense? And then like how many size 5 subsets are there? Well, size 5 is the whole darn thing, and so there's just one option, right? It's just that one set, just one, all right? And now the question is like, what about size 3? What about the size 3 subsets of a size 5 set? Like you got 1, 2, 3, 1, 2, 4. Remember that order doesn't matter. Like this is equal to 3, 2, 1. They're the same set, so you don't want to double count, triple count. That's not okay. And so that gets hard, right? So now let's figure this out. How many size 3 subsets are there of a size 5 set? Let's do this. All right. There is a trick. All right. We can think about it. It's very close to the answer if we just talk about permutations, right? We know how to do size 3 permutations, right? 3 permutations of a size 5 set. Like that's a thing. We know that now. Permutations almost get us there, right? Because we can ask for like, what's the size, the number of 3 permutations of a size 5 set, P53. That tells us how many length 3 permutations of that set there are, right? But then you overcount, right? Because like you're enumerating all these size 3 options, right? You can choose like 1. Let's do this one. Like 1, 4, 5 is an option, like that comes out. And then also though, like 1, 5, 4 is the next option right after that, isn't it? But if we're counting sets, right? These are the same set. Yes, we're overcounting. Now the question is, how many times do we overcount? All right, so like, think about just 1, 2, 3. And we're taking 3 permutations. Like we see it this way, just 1, 2, 3. We see 1, 3, 2. Those are that's in the 3 permutation. 2, 1, 3, 2, 3, 1, 3, 1, 2, 3, 2, 1. Those are all right going to appear, and those are all the options, right? But those stand in for just that one set. So we counted it 6 times if there's 3 things. Where does the 6 come from though? It's all the ways of jumbling 3 things. Yes, does that make sense? Like the order of that size 3 subset that we're trying to enumerate, it doesn't matter, right? It's just like these are all equivalent to one another in terms of sets. And so we're going to see it, if it's the size 3 thing that we're taking, we're going to see it. How many ways are there to jumble 3 things? 3 factorial times. That we're going to end up overcounting each subset, if it's a size 3 subset, 3 factorial times. So we want to divide, right? We want to divide then by that. Do you see it? We just want to count them once. So yeah, we just want to divide by the factorial of the subset size. So that's your answer. Like how many size 3 subsets of a size 5 set are there? Start with the permutations. That'll get you most of the way. Like the count is equal to P53. That'll count all these options, but we've overcounted by each size 3 subset 6 times, right? Like divide out all the jumblings of each of those things. All right? So over 3 factorial. And so if you think about it, what's P53? That's 5 times 4 times 3, because you're choosing 3 things from a size 5 set, but you're overcounting each of them. They're duplicating things that many times, so 3 times 2 times 1. And so the 3's cancel. It's 20 over 2. So that means there is exactly 10 size 3 subsets of a size 5 set. Does that make a little bit of sense? Try to enumerate them. That's a thing. But that's now something we can count. And then the permutations almost got us there, but we overcounted, so we have to divide by how many times we're overcounting, all the ways that we'd see things. And it has to do with the size that we're creating, all right? We divide by that. That's called a combination, okay? It's called a combination. And instead of PNR, we say CNR, the permutation combination. So CNR is short for the number of R subsets or R combinations. That's why we use C in a set with N elements. All right, there's a bunch of different ways to notate this, by the way. CNR is a thing. Other people draw it like this. This is a very common way to see it. We write this one. See, this stands for CNR. It's the number of R subsets of a size N set. But the way that we write it like this, we say it differently. We call this N choose R. All right, it's a shorter idea. It's like you got N things total. You want to choose R things out of it. Does that make sense? You're choosing R combinations of a size N set. So N choose R. That's what the syntax says. All right, and so we have just determined, like the formula for it. It's like PNR over R factorial, which, like, if you simplify it, becomes that. You can memorize that if you'd like. What we've just learned is the like CN or C53. Yes, that's what we just figured out. We just solved for C53, the number of size 3 subsets of a size 5 set. So we noticed that 5 choose 3 is equal to 10. All right, we did the math. And yeah, no repetitions are allowed. So like how many ways are there to choose things? Where you can't have duplicates, and then repetitions aren't allowed, and then order doesn't matter of an original size set, size 5 set, for example. Okay, so yeah, every combination that you pick, right, is just a set. Like, all right, I picked this set, this set, this set. Those are my individual combinations, and you've probably learned this before. Like, I remember learning this idea from like a high school class, but they never talked about set theory back then. So really, secretly, your math teachers were just talking down to you. They were condescending, and they were like, this is what they meant, right? When they said order doesn't matter, and then just like moved on with the lesson. They were talking about, we were picking out sets, all right? That's the secret. Now you know it. That's combinations. Your turn. So, okay, let's say we got this set S. It's got these characters in it. How many subsets of S have either 2 or 3 elements? All right? So it's a combination kind of question with some extra secret sauce. But see if you can figure that out. How many subsets of S have either 2 or 3 elements? All right? So here, if you want a hint, keep the video rolling. So like, what are some size 2 sets? Like AC is an option, BD is an option, so like all those, and then also like a bunch of size 3 subsets. That's what we're considering, right? I maybe have given away some of the answer, like ACE, BDE, all the size 3 ones as well. Can you see how to figure that out? So I think the easiest way would be to separately count the size 2 ones and separately count the size 3 ones. So separately, count the size 2 subsets and the size 3 subsets. Do you see it? That'll do it, because then, all right, we have a size 6 set. We want to know how many size 2 subsets of them are there. That's 6 choose 2 plus all the ways to make a size 3 subset out of a size 6 set. So it's 6 choose 3. 6 things, choose 3 of them. How many ways are there to do that? And so if you think about it, all right, to choose 2 things out of a size 6 set, you got, well, how many permutations of 2 things are there? 6 times 5, right? 6 options for the first thing, 5 options for the second thing. But then how many times do we overcount? Twice, right? Because you see AC, then you also see CA. It's 2 factorial times, right? So just 2 times. 2 times 1 plus the same thing. Like how many size 3 subsets of a size 6 set are there? That's, well, do the permutations first. 6 times 5 times 4. Those are all the jumblings of 3 things, but we've overcounted each of those 3 things 3 factorial times. So 3 divided by 3 times 2 times 1. All right? And so there's going to be, if you do the math, there's your final answer. Does that make sense? That's kind of cool, right? So it's like sum rule, product rule, generalized product rule, counting combinations, counting permutations. You can combine these ideas, okay? And we did. So, okay, let's keep on going. Let's consider now permutations where you can repeat things. This is a little different, all right? So a permutation with repetition is when you're ordering a set, you're jumbling things, but some of those things you can take twice or 3 times maybe. Like things are identical. So a good example is like you're trying to permute the letters of a word and there's some duplicate letters. So like permute the letters of lol, for example. So what we'd like to do, right? Some of those permutations are going to be like counted twice. Because if you think about it, like you want to permute the letters of lol. So you got 3 characters, right? You can consider like this is the first L, the O, and like the second L. But if you just try to do normal permutations, right? You're just like, all right, it's 3 factorials the answer. That's not right because like you do this permutation L1, 0, L, or O, L2, and then you have L2, O, L1. Those are 2 separate permutations, right? They're considered to be separate if you're counting just permutations, but they're really just both lol, yeah? They should be considered equivalent. Do you see the problem there? So you can't just count, all right, it's a size 3 set, let's permute it. The answer is not 6 because these are the same string as far as for all intents and purposes, yes? So really, what's the right answer? If you think about it, it's like, all right, it's LOL, LLO, or OLL. There's only 3 options, actually. Does that make sense? So there's, like, some of those permutations are the same as others, and we don't want to double count them. Like, there shouldn't be, it's not the case that, like, the first L, O, the second L is different from the second L, O, the first L. No, they're both LOL. Yeah? So I hope you see that. And so, if you think about it, what are our options? Let's see. Do I want to show it to you now? Kind of. Yeah, let me show it to you, and then we'll do a larger example. So I want you to think about it this way. Like you're filling in, like you're permuting things. You're filling in blanks. All right, so you got 3 blanks for lol. You're permuting all the letters of it. You got 3 blanks, and so like give them numbers 1, 2, 3. If you think about it, like where could you choose first the duplicate things? Like we want to choose where to put the L's first. All right, how many spots are there to fill for the L's? Yes, there are 2 L's in my string that I'm trying to jumble. Those are my duplicate characters, and I'm just trying to choose indices to place them. Does that kind of make sense? So at the beginning of time, when I've made no choices, I've got 3 options total, and then I've got 2 spots to fill. And it's a combination, it's a subset kind of thing. Does that kind of make sense? There's 3 choose 2 spots for the L's. Because it doesn't matter the order in which you choose those indices. Does that make sense? It's like either, all right, the L's are going at 1 and 2. Like we're choosing sets. It's not like put the first L index 1, the second L at index 2. It's no. Choose 2 indices, like the set 1, 2 is where both L's are going, because order doesn't matter. Do you kind of see it? That's the secret. And then after you've done that, there's 1 spot left for the O. Spot left. So your hand is forced. For the O, there's only 1 way to fill in that. And so 3 choose 2 is the final answer. It's 3 choose 2 times 1. Does that make sense? And so that's why the answer is 3. Okay? Let me spell that out further in another example. So let's count all the ways to permute the letters in the word Beyonce. All right. So we got some duplicates. We've got 2 E's again. All right. And so here's how I want you to think about it. We've got we're permuting all these letters. It's essentially like each time we're trying to compute a permutation, we're trying to fill in blanks. All right. So there's 7 letters in that word. Yes. 7 total. And so think about it in terms of indices. You're filling in all these indices. Start at 1, start at 0, doesn't matter. You always want to pick the duplicate things first. So like you've got 7 locations, right? And 2 E's to place. And the order of those E's don't matter. It doesn't matter like the first E comes before the second E. No, they're E's, okay? So this is a combinations question for the E's. There's 7 locations to fill in with those E's. Does that make sense? So 7 choose 2 options for your indices to place the E's at. It's like, all right, I'm going to place an E here. I'm going to place an E here. It doesn't matter like which one was the first E and which one was the second E. The order doesn't matter. Just like choose 2 indices, like index 2 and index 5. That's a subset. Does that make sense? So there's 7 choose 2 options for the E's. And then now, depending on where you put the E's, you still have 5 blanks somewhere, right? 5 more letters to fill in, and those are not duplicated. None of these are duplicated at that point. So like, there's just 5 letters left in 5 locations, so there's 5 factorial things to do after that. All right. Do you see how like it's the product rule after that? It's like, all right, I got 5 things left to fill in and 5 factorial options for each of them. You see it? 5 factorial options to fill in the remaining 5 blanks. So here's how many ways there are to fill in the first, fill in the duplicated letters, because order doesn't matter. We don't want to duplicate, so we count without repetitions or anything, like order doesn't matter, subsets, and then we count permutations of the remaining letters that are all different. So that will be your final answer. I hope you see it. Okay, so there is a formula for that if you want to think about it. But honestly, I like this explanation. Like you're filling in things, you're thinking about the duplicates. You're choosing indices at the end of the day. So here's the main formula though, if you want to think about it this way. Let's talk about Mississippi. We want to scramble all the letters of Mississippi, and there's a ton of duplicates there. So, okay, how many letters, first of all, are in Mississippi? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So we got 11 slots to fill in. All right, let me draw 11 boxes. Giving me carpal tunnel just for you guys. 5, 6, 7, 8, 9, 10, 11. We got 11 indices then. 4, 5, 6, 7, 8, 9, 10, 11 slots to fill in. And all right, how many, like we got Mississippi, how many M? Let's count all the letters, right? There's 1 M in Mississippi. There are a few I's. There's 4 I's, right? 4 I's. There are a lot of S's as well. 4 S's. There's, what's left? Just P's, right? And then 2 P's. Does that add up to 11? 8, 9, 10? Yeah. So those are the letters we're trying to fill in. If you think about it, in the way that I've shown you so far, you can get the answer. It's like, all right, pick which character comes first. Like, think about the duplicates first is a good idea. It's like, all right, let's place the I's first. We've got 11 slots to fill, and we got 4 I's to place, and the order of those I's don't matter. It's just like, was there an I or wasn't there an I? So at the very beginning of time, it's 11 slots to fill and 4 I's to place. Does that make sense? So I got 4 I's to place, and you can place them anywhere because we haven't done anything yet. So you can choose who comes first, like pretend it's the I's. So you got 4 I's to place. And you could do this, start with the S's or the P's, doesn't matter, it'll still be equivalent. Still be the same answer. 4 I's to place. And so like you're gonna place 4 I's, right? The first, some I's go there, some I's go there. Like who knows what happened, but like that's where they ended up. Something like that. All right, there. So I placed some I's. And now how many slots are left is now the question. Like wherever you put the I's doesn't really matter because you still have 11 minus 4, right? Is that 7? There's 7 now slots left. 7 blank slots to fill. Wherever you place the I's does not matter. This is all generalizing. So you're going to keep multiplying, right? So now it's time to place something else. Place the S's. So now let's place 4 S's in the remaining slots. How many are there? The order doesn't matter. It's like we choose 4 indices that are left, whatever they are. 7 slots left. There's 4 indices to place my S's at. You see it? 4 S's. So kind of see how it's generalizing there. And then, all right, I've placed my S's. Who knows where they went? You put one there, put one there, put one there. Now we have to fill the remaining slots with the remaining letters. And we cancel out any duplicates. So we got like, how many slots left? 1, 2, 3. Just 3 slots left, right? Oh, did I mess something up? I see 4, but there should be 3. Sorry. Yeah, there were 4 S's to place. Excuse me. So let's say I placed another S there. There we go. 4 S's and 4 I's. Sorry if you're screaming at me through the screen. But I've placed my 8 letters so far now. And so I've got 3 slots left. Whatever they are does not matter. We're just going to multiply because it's all going to generalize, right? Generalize product rule. So, okay, 3 things left. Let's place the P's. All right, so I've got 2 P's and 3 slots to place them at. The order doesn't matter, so it's a subset question. Pick me 2 indices, please, out of a size 3 set of remaining indices. Do you kind of see how I'm reading that? So you got 2 P's to place after that. 2 P's. 2 P's. And, all right, you place them. Maybe you put one there. You put one there. And then you got 1 slot left for the M, right? The order. Pick any order, right? And so your hand is for, there's only one place to put it after all that. So there's like times 1 for the M, right? That's where you're placing the M. There's 1 slot left for the M. And so you can think about that as like, all right, I've got 1 option, 1 slot to fill and 1 thing to put there. the answer is 1. Still 1 choose 1. This technically would work for you. But that's the secret, right? That's why it works. And so there is a nice formula in your textbook, and I will show you the formula and how it gives you the same answer as this. But let's see here. Let's try to write out this formula. So like 11 choose 4, what is that? So, well, you're choosing 4 things, so 11 times, it's going to be, I guess we can do this formula, can't we? This one, it's going to be CNR, n choose r is n factorial times r factorial times, so over r factorial times n minus r factorial. Let's do that one. So, okay, 11 choose 4, what is that? That is 11 factorial over 4 factorial times 11 minus 4 factorial. So that's 7 factorial. And that's that times this guy, so that's 7 factorial, according to the formula, over 4 factorial times 7 minus 4 factorial, so that's 3 factorial, times 3 factorial, which is 3 choose 2, which is 3 factorial over 2 factorial times 3 minus 2 factorial, which is 1 factorial. And then if you want to play this game, like the 1 is just 1 choose 1. So it's like 1 factorial over 1 factorial times 1 minus 1 factorial, which is 0 factorial. Is defined, though, 0 factorial is defined to be just 1 in math. So like that goes away to 1. But do you see how like a lot of things are canceling? Like the 7s cancel, the 3s cancel. So this is how you come up with the general formula. Like this, there's going to be 0 left at the end. So that becomes a 1. And so in general, if you assign each character in the string a different number, this is what they think about. All right. So the number of distinct sequences with n1 ones is pretend that the m was a 1. Like every separate letter was really a number. This is what the book is trying to say. N1 ones, N2 twos, turn it into a bunch of digits, digit strings, NKKs, where the total size of the string is equal to the size of the number of the first characters, second characters, K characters, is equal to size of the string factorial over the first option factorial, sum of the first option factorial, like the number of duplicates for the first thing, the size of the duplicated characters for the second thing, all the way down. And if there are no duplicates, it's just 1. The number of those characters is just 1. So that's the NKs, or the number of that many characters. And so for us, it's just this. Like you got, all right, the size of the string I want to permute and jumble is 11. So 11 factorial over all the different permutations of those individual pieces. All right. So that's what's going on. It's factorials. So it's like, all right, there's 4 i's, 4 factorial. There's 4 s's, 4 factorial again. There's 2 p's, so 2 factorial, and then there's 1 m, so it's just 1 factorial. Is your dividing by. So that one goes away, of course. But that's how you end up with that formula. I hope that makes sense. So that's what happens. That's a general way to think about it if you'd like to think about it that way. And I think that's all that I want to say. Your turn. All right. How many ways now, using this idea, I want you to really think about it. Try to get it this way first if you can. Don't just memorize the formula. That's not as useful, I think. But you can check yourself with the formula. How many ways are there to permute the letters in the word college? So think about it. Well, how many letters are there? You got, how many slots are there to fill? 7 slots, right? And then how many duplicates do we got? We've got 2 L's and then 2 E's. Those are other things that are duplicated. So all right, we got 7 slots to fill at the very beginning. And let's place the L's first. So we got 2 indices to choose to place them. Then you filled in 2 characters. You got 5 left. All right. Then let's place the E's. You got 5 slots to fill, or 5 slots to choose from, 5 indices to pick where to place the E's, and 2 E's to place. Give me all the different ways to do it, where order doesn't matter, because they're the same letter. So times that. And now I've made 4 choices. I got 3 things left, and those are all unduplicated characters. And so it's just like 3 factorial after that. Does that make sense? But that's equivalent to our formula that we just found. It's going to be equal to 7 factorial. Do the math, and it will work, over all the different letters and their combinations. Like, all right, I had over 2 L's, so 2 factorial, 2 E's, so another 2 factorial, and then everybody else was unduplicated. The other 3 letters were unduplicated. And so the count of them was just once, like 1 factorial times 1 factorial times 1 factorial. And so those kind of go away to nothingness, but that's why it works. So these are exactly equivalent, I promise. That's not a very good equal sign, so here, let me redraw that. But that's the answer. Did you get it? All right. yeah, one of the last things I want to do today is talk about multisets. I'm going to count all the multisets. So a multiset is very similar to a set, but duplicates, you finally can have duplicates. All right, they can finally exist. A multiset is a collection that can have multiple instances of the same kind of thing. So we do consider the same thing indistinguishable, so that order still doesn't matter for those duplicates, which will make sense with examples, I promise. But for example, in a multiset, you can have this. You can have 1, 2, and 4 sevens, and that's not the same as the multiset 1, 2, 7. So it's not sets anymore, it's multisets. You can have duplicates. Like the fact that you had 4 sevens matters now. All right, isn't that cool? Because yeah, multisets is useful for certain tasks. Like you can imagine that you want to use multisets when you talk about the bills in your wallet, right? You want this multiset, and you don't want it to be the same as this set, right? This multiset, obviously. So okay, let's try to figure out how to count multisets. So here's like the kinds of problems I want to teach you how to solve. So like, given like an infinite supply of parts or pieces, try to fill like a basket. Like you got your shopping at like Costco, and Costco has an infinite amount of things, and I want you to figure out how to fill a basket of n items. Like you can choose n items from m different varieties, m different items at the store. All right, you can choose as many of those. Like you can choose n things from just one variety if you wanted to. Like they have as many as you need of any of them. All right, so here's a silly example. So like you've got a basket and you're trying to fill your basket. All right, it's like Easter, something like that. And you're trying to put stuff in it. Like I can take some of those things, some of these things, some of these things. Like you're just trying to fill it up. You can take as much as you like. So here's my silly example. Let's say that we've got a basket and we're putting puppies in the basket. All right, so our basket can hold 10 puppies, 10 dogs, and we have 4 breeds to choose from. All right, so let's say, and we're going to consider dogs of the same breed to be indistinguishable. Like how many ways are there to place 10 dogs in a basket where you can have 4 different breeds to choose from for your dogs that you're trying to pick? All right, so like 4 different options. Like you can choose from a bunch of golden retrievers, a bunch of labs, a bunch of chihuahuas, a bunch of poodles. Like that, maybe those are your 4 options, for example. And you can choose, like one option is like you choose 10 golden retrievers. Maybe that's what you want. 10 labs, that's fine. Those are certain baskets. But like how many different kinds of baskets could you have? All right, that's our question. Now here's the answer. Here's the kind of the formula. All right, so the secret is you think of your basket, your options, as your choices that you've made as your final basket as a binary string. All right, it's a little weird, but let me show that to you. So you've got 10 dogs to choose. And I am not writing very legibly today. I'm very sorry. 10 dogs to choose. Let me just rewrite that entire word. 10 dogs to choose. And then you have 4 breeds to choose from. If you think about it, you can turn this into a binary string in the following way. All right, you just decide that there's an order to your breeds. Like first it's golden retrievers, then labs, then chihuahuas, then puppies. So pick an order. That's fine. And then start putting tally marks for each. Like you've got a basket made. Put tally marks next to how many you got per breed. All right, so like put 1s to mean 111 means I got 3 of the first category, like 3 golden retrievers. That's my first category. And then when you're done with that category, you put a 0 to separate. The 0 is now your separator. All right, does that kind of make sense? Like 3 from the first thing, and 0 is my separator. To me, now I'm talking about the next thing. Does that kind of make sense? And then, all right, maybe I choose 1, 2, 3, 4, the next breed, the Labrador, 4 labs. And then to mark that I'm done choosing labs, I put a 0. If I don't want any of the next breed, I just put another 0, like move on to the next one. But maybe I want to take like 1, 2, what was the next one? Chihuahuas. And then 0 to mark off the next one. And then I always have to choose 10 dogs. So like how many have I chosen so far? 7, 8, 9. So I got 1 left. And I put a 1 to mean that. So I always have to do that. But do you see how you can turn your choices, your baskets, into these binary strings that mark like that? After you've chosen an ordering for your breeds, for example, for your items to choose from. That's the trick. And do you see how there's always going to be, if you're building binary strings like this, there's always going to be as many 1s as there are things to choose, so 10 1s, and then there's also going to be 3 0s. Yeah? So your strings are of size 10 plus size of breeds minus 1. So 10 plus 3 is 13. Yes? Does that kind of make sense? So the number of ways, in general then, to select n objects from a set of m varieties, like we got 10 puppies and 4 breeds, four varieties, is count how many ways there are to build a string like this. You've got a bunch of ones and zeros. You know that your string has to be exactly size, what is it? 13, right? So you got 10 dogs, and then there's 3 separators, right? For your 4 breeds, 4 minus 1. So that is going to be a subset kind of counting question. So n plus m minus 1, so that makes 13, right? Over m minus 1, which is 3. And that's going to be your answer, because you can turn this problem into like how many different binary strings that look like this are there. You can think of it as like all you need to do, like you've made a basket, you've described a basket by just picking where the zeros go. Does that kind of make sense? That's the trick. Like you've got a size 13 string, and just pick where the 3 zeros need to go, because you got to have 3 zeros to section off your choices. So the answer is 13, choose 3. All right, this is equivalent then to picking where the zeros go in the string. You can also turn this into checking the ones, and those will be equivalent answers. But the zeros are fewer usually. So picking where you want the zeros to go. So yeah, or you want them to go in the string. Because the rest of the slots, once you've picked where the zeros go, the rest of the slots are forced to be ones. Do you see it? You're forced to have always n ones, because you're picking n things. Yeah? So that's the secret. That's how you do it. All right? So I guess I did this out of order, but hopefully that makes sense to you. All right? So now it's your turn to try that. So, okay. Oh, sorry, excuse me. This one is not a question about multisets. I guess I'll ask you one maybe later. This one is a previous concept, so maybe this kind of thing again, or just a remainder question of like a combination of things. So this one is not about multisets, but it's still a good question to ask, I promise. So how many different strings of length 12 contain exactly 4 Bs? All right. Only though you get to choose from the alphabet A, B, C, D, so not all the way to Z anymore. So how many strings of length 12 using these characters have exactly 4 Bs? Can you count them? All right, so it's kind of like this one again, maybe. Counting permutations with repetition. Multisets are kind of like combinations with repetition, aren't they? So, okay. There is a pattern here. So we've got 12 slots to fill again, right? 12 slots to fill. 1, 2, 3, you can number them. Is that what you did, maybe? And then you have to have exactly 4 Bs. So do you see how, like, maybe you should choose the slots for the Bs first? Like you've got, all right, at the very beginning of time, you got to place 4 Bs somewhere. You got 12 slots to fill because they're all blank right now. And there's 4 Bs, and the order of them don't matter. It's like pick your 4 slots for the Bs. And then do you see how like you have an easy way to do the rest? So after you've picked your 4 slots for the Bs, you've got 8 slots left to fill in with the character, and you can only pick non-B characters at that point because you force the Bs. You got 4 of them, can't have any more nor less. So place the Bs, and then you can have whatever you like for the rest of them. You got three choices, A, C, or D, for all of the rest of the slots, and you've got 8 slots left. Do you see it? So after that, like, that's why it's only 3. You can only choose from A, C, and D. Those are your characters that you get after that, and that's going to be your final answer. I hope that makes sense. Okay, yeah. So I think that's where I want to stop today. I'll give you a question about multisets next time, but that's enough for today's lecture. I hope that was fun, just like bringing things that you've probably seen. Some of these things you've definitely seen before, but bringing them back to set theory so we can study them more in detail. So it's a fun little topic for me, at least. I hope that you think it's fun too. And I think that's all that I've got. So I'll see you in the next one.